hear me?
Yeah, Tama, we can hear you fine.
Thank you. Yeah, it's my slide. Yes, MMX. Thank you. I'm gonna start. Okay. I'm starting. I'm delighted to present the third Japanese sample return missions following the Hayabusa and an ongoing Hayabusa 2. The next to these asteroid sample return mission, the JAXA select forward sample return called the Martian Moon Exploration (MMX). And today I'm giving a quick overview of MMX and including the mission profile, instrumentation, science goals, and the current status. Next slide, please. Yeah, here's a timeline of MMX, and it's a great news in the February 2020, 2 months ago, that JAXA officially approved the MMX as a mission. Now we are in phase B. So the MX mission plans to launch in 2024 and goes to the Phobos and do some remote sensing and in situ observation. And also, we're gonna do multi flybys on Deimos, do some remote sensing observation, and we will get the samples greater than 10 grams of the Phobos regolith and return to the Earth in 2029. So the MMX could be the first sample return mission from the Martian satellite Mars system. So next slide, please. While we go Phobos and Deimos, the point is that the regoliths of Phobos and Deimos contain the Martian building blocks, impactors, late accreted volatiles, ancient Martian surface component. Click next slide, please. So, therefore, the Phobos sample return mission is expected to contain the initial condition of the Mars Moon system, and also, please, next, please. Next slide, please. Sorry, one more. Yep, and also the Phobos sample. Go back. Sorry. Yeah. Yes, Phobos sample also contain the vital insight and information on the sources and delivery processes for water and hopefully organics into the Mars and the inner rocky planet. Next slide, please. But before going that, we should identify the origin of Phobos and Deimos, because there is a two competing hypotheses are still proposed. So MMX has two major goals. One is to reveal the origin of the Martian moon, which will make progress in understanding the planetary system formation. The other goal, the goal two, is to observe the processes that have impact on the evolution of the Mars-Moon system. As you know, the lunar Apollo mission provided significant knowledge not only for the moon but also the Earth as well, like a magma ocean hypothesis. In the same manner, we hope that and we believe that exploration of the Martian moon will also provide the essential information on the formation and evolution of Mars. Next slide, please. Next slide, please. Yes. Yep. Thank you. It's the planned mission. Oh, sorry. Go back. So there is some delay. So. One more, but page 5. Thank you. Here's a mission profile. The total of 5 years trip by using the chemical propulsion system. So interplanetary flight in 1 year, and for outward and homeward, and stay at the circum Mars orbit in 3 years. For example, we will launch the spacecraft in the summer of 2024. Then we'll take about 1 year for outward interplanetary flight. The spacecraft will stay at circum-Mars orbit about 3 years for exploration, followed by the 1 year homeward interplanetary flight to Europe. During at the circum-Mars orbit, we plan to land on Phobos at least one time to get the samples of more than 10 grams. So next slide, please. This slide shows the spacecraft configuration. As a result of the Phase A study last 2 years, the spacecraft configuration and the major specifications are defined almost preliminarily. And the total launch mass, including the propulsion, is about the 4,000 kilograms. That consists of the three modules on the left side, exploration modules and return modules, and then propulsion modules. As I said, we will use the chemical propulsion systems, chemical propulsion for Mars orbit insertion, injection, and also the escape maneuver. Next slide, please. We selected 7 nominal size payloads for remote sensing observation and a rover that is equipped with the 3 instruments. Very, very much instrument-rich mission is MMX. So the size payload includes the wide-angle multi-band cameras and also the telescopic cameras. We also have a gamma ray and neutron spectrometer provided by US, the APL, Johns Hopkins University. And also that we have a near infrared spectrometer provided by the French group called MIL. And also the light detection lensing LiDAR, and also the dust monitor CMDN, and also we have mass spectrometer analyzer. The spacecraft also carries a sampling system equipped with a robotic manipulator, which enables the acquisition of the Phobos regolith 2 centimeters beneath the surface. Next slide, please. The origin of Phobos and Deimos are still a matter of significant debate, as I said, and the 2 competing hypotheses are proposed for their origins. One is the capture of asteroids, which is supported by D or T type infrared spectra. The other hypothesis is an in situ formation by an impact, somewhat like Earth's moon formation. We call like a giant impact, which is consistent with their dynamical properties such as low eccentricity and inclination. Next slide, please. Yes, the figure on the left shows the near-infrared spectra of Phobos surface in blue, compared with those of the carbonaceous chondrite. As you can see, the surface of Phobos has very, very smooth and featureless spectra, also a very low reflectance, like a 0.003 or 4-ish, almost black. And these features are similar to those of D or T type asteroids. Such a D or T type spectrum is consistent with their captured origin. If the Phobos and Deimos but actually a giant impact origin instead, these spectra reflect either just an impact-related dark glassy debris or thin surface regolith veneers or just the result of the space weathering? Next slide, please. So these kind of questions will be tested by MMX, as we have the gamma ray spectrometers, a new instrument, and also we have a sample back to the Earth. Next, please. But on the contrary to the spectral features, dynamical properties are consistent with the impact origin. Phobos and Deimos have very low eccentricity, like 0.00 something, as well as the low inclination, like 1 point something degrees. Such a low eccentricity and inclination clearly suggests the impact origin. But if the Phobos and Deimos are captured origins instead, next slide please, it should be a goldmine, I think, for astrophysicists, because we need a new dynamical model to reconcile a competing hypothesis and also the MMX observations. Next slide, please. Yeah, here's a quick overview of the remote sensing observations that will be done by MMX. We have, as I said, we have many instruments. That is the key instruments are the visible and near-infrared spectroscopy, which will provide the critical data set to determine the origin of Phobos and Deimos. For example, the visible near-infrared spectrometer, for example, MEPAG is an infrared spectrometer, will map out the distribution of the hydrous minerals and organics with a very high spatial resolution. Let's say 7 meter per pixel from nominal altitude of like 20 kilometers. Figure on the right shows gamma ray and neutron spectroscopy. We call the MEGANE, is the name of the instrument provided by APL, Johns Hopkins University. The gamma ray neutron spectrometer MEGANE will provide the abundances of the hydrogen, oxygen, silicon, iron, and hopefully other elements like calcium, potassium, these kind of elements, which will hopefully clearly differentiate achondritic and chondritic compositions. That will be the very important key to identify the origin of Phobos building blocks. Next slide, please. Yes, this table shows the expected characteristics of Phobos return samples coming out from my papers in place in Space Science Reviews. In terms of the petrology, mineralogy, the bulk chemistry, and isotopes and organics. As I said, we don't know much yet about the origin, so there are lots of options, assumptions for the origins. But the remote sensing data will provide the basic information about the petrology and the mineralogy and about chemistry. And also the next slide, please. MMX is a sample return mission, and an isotopes will provide the most convincing evidence to differentiate the origin of Phobos. For example, the figure on the right shows the chromium-54 isotopic composition versus the capital delta 17O. These are palmulates and also the part-per-million difference from the terrestrial values. There is such a very faint difference, but these isotopes clearly show that the samples from the achondrite, chondrite, and then the carbonaceous chondrite, Earth and the Moon, all these planetary materials have different isotopic signatures. Once we get the sample back to the Earth, we will determine get these isotopic compositions that would differentiate the origin of phobos building blocks. Thank you. Next slide, please. Another interesting point is that the Martian Martian samples may exist in the regolith of Phobos. Figure on the left shows numerical simulation results showing the spray of the impact ejecta on the Phobos orbit. These numerical simulations suggest that the Mars impact ejecta could exist in the regolith of Phobos. Next slide, please. And also the further recent paper by Hyodo et al. Shows that the Mars ejecta on Phobos is expected to experience a much lower launch velocity than the Martian meteorite. Hopefully preserve the original information. And next slide, please. Then also contain a variety of ancient sedimentary materials such as the calcium sulfate found in the Gale crater. Next slide, please. So I hope that the Phobos regolith provide a wealth of information on the ancient surface environment of Mars. Next slide, please. We have 3 more slides. Yep, here's a cartoon showing the sampling system. We have 2 systems. Next slide, please. One is a coring system that would access the Phobos building blocks beneath the surface, which is totally different from the Hayabusa and Hayabusa 2 system. The other is a pneumatic sampling system provided by the Honeybee Robotics that would selectively sampling of the Phobos surface veneers. Sorry, next slide, please. Yep, is what I'm talking about, the pneumatic sampling system. So next slide, please. Last slide. So as I said, we are going to get the Martian Phobos samples greater than 10 grams. And also MMX team will use the 1/10 of the return samples, which contain the 10,000 grains, assuming the typical grain size of the 0.3 millimeters. 100 grains are selected will go for the detailed petrology, mineralogy, and an in situ isotopic analysis. Then the further selected 10 to 20 grains will be used for the destructive, the bulk isotope analysis. And the point is that we will plan to distribute it more than 90% of the return sample to the international community. Next slide, please. Here's the conclusion. The MMX spacecraft scheduled to be launched in 2024 and return the Phobos sample back to the Earth in 2029. The origin of Phobos and Deimos has been in debate, captured asteroid or in situ formation by impact. And thirdly, the MMX will provide a cruise to their origins and offer an opportunity to directly explore the building blocks, the juvenile cross-mounted component, and late accreted volatiles of Mars. So next slide, please. Finally, MMX will constrain the initial condition of the Mars-Moon system and shed light on the source, timing, and delivery process of water into the inner rocky planet. Thank you. Oh, next slide, please. One more thing. Yep, that's it. Thank you.
All right, thanks, Toa. I appreciate that. I know if you're looking at the clock, folks, we're probably going to have to go through our break. But what I'd like to do is to just allow people who would like to ask questions over the next 4 minutes before the next talk starts to do so. Just a quick thank you to our friends at in Europe, where I know it's, oh gosh, what is it? let's see, if it's 1 p.m. here, it's something like 6 or 7 p.m. there. I know it's 9 p.m. in United Arab Emirates, and it's 2 a.m. in Japan. So thank you
Yep.
very much for coming and speaking. So we've got a couple minutes for questions for Tomo or any of the other speakers.
Okay, I think that all of the UAE questions were answered in the chat, but I have a few here for Tomo. The first one was from Carol Stoker. It seems like a Phobos sample return has a lot of overlap with the Mars orbit aspect of a Mars sample return. Is there any plan for Japan's involvement in the MSR, the Mars sample return campaign?
Yep. It's a top-level arrangement, but it's the Japan. Actually, I'm from JAXA. JAXA really interested in the MSR. So JAXA is now going to step into the trying to get involved the Mars sample return in the last stage, not like exploration of the spacecraft, but it's the try to involve in the analysis of the samples, like contribution to the sample receiving facilities and an instrument in them. So we are now keen to develop the very continuous sample return plans, not only for MMX, but also the MSR, but from the Hayabusa 2, and OSIRIS-REx, and also MMX and MSR from the 2020 to 2030. So we have already started the conversation with the NASA folks about that. Thank you.
Great. I also had a question. Is there any anchoring system for the surface platform, and how do you prevent rebound?
Oh, it's a pretty much critical question. Then our engineering team have worked extensively on that. We have one of the idea we have is now that kind of a cushion, shock absorbers made by metallic honeycomb structures. And as far as I know, I heard from the engineering team that honeycomb structures, the cushions, does pretty much work well. So we don't have any specific anchoring system, but there is we have a kind of cushion. Thanks.
Okay, another question from Abigail Freeman. I'm very excited about MMX. Are there any plans for an international participating scientist call for this mission?
Yes, of course. We are now contacting the NASA's and also the ESA's and also the agencies in Europe. It's a pretty much already international. So I guess for sure that the participating scientist call will come out. Thank you.
Great. There was one more comment, slight kind of question. It says, I'm surprised that there doesn't seem to be a thermal IR radiometer for surface thermophysics. Was that something that was considered?
It was considered, but that's an instrument was not selected because of many reasons, including the mass payload mass limitations. But we have a rover, small rover, provided by CNES and DRL. We'll have that has instrument that will give us an thermodynamic property, but it's not like thermal infrared spectrometer, something like that. Yeah, that was a tough decision.
All right, thanks very much
thanks
again.
so much.
Yep, thanks everybody for calling in at whatever time you called in. We appreciate it. Let's move on to